All right, guys. So today we're going to calculate the stresses after we know the load. So let's write over here stresses. All right, so let's do maybe a little summary of the problem. So our problem is we had a cantilever beam. Of 0.4 meters. I mean, we don't need that information, but it doesn't matter. What's important to know is that we had a force over here of 13 kilonewtons and a force over here of 9 kilonewtons. The current system we use, if I remember properly, X, Y, and Z. So now, at the root, which means that X equals 0, which is over here, we have that what? I mean, I think I have it here open, but basically the moment will be the reaction moments, or you can take here at MBZ. So embedding moment Z at X equals 0 will be minus 5.2. Here I'm just going to put the magnitude. So let's say bending moment BZ is 5.2 kilonewtons per meter. And the other one, okay, so this is a 5.2. I guess what is the other one? MBZ. Okay, and MBY will be equal to 3.6. Okay, let me go here to see what is really the direction of those moments. So let's see, 5.2 and 3.6 counterclockwise. And this one is also counterclockwise. So really both of them. Okay. All right. But again, we can look at it from the forces. So it should not be that problematic. So now, where do we need to calculate the stresses? If we look at the cross section, so looks like point A is over here. Point B is over here. And the distance between A and B is 60 millimeters. And again, this should be the neutral axis. This is 150. What else do we know? T is 30 millimeters. And the total depth is 75. Okay. So let's first do point. Let's do both points at the same time. I'm going to need your help, but let's say like coordinates of points A and B. Okay, point A. Oops, we now have is Y and Z. So basically, remember, right? We had here, this is Y, this will be Z. So let's see, if we look at point A, what should be point A? Should be, I'm just gonna put the magnitudes, okay? So the Z should be 75 millimeters, which will be 0.075 meters. No, will be half of 150. Okay, imagine the original reference frame is here. This is Y. This is Z. So will be 150 divided by 2, which should be 0.75. And the Y, again, this will be the same thing. The Y will be, oh no, will be 75 divided by 2, which is 37.5, which will be 37.5 millimeters. What will be 0.0375 meters. Okay, and point B. The Z will be what? Will be the point Z, will be the 75 minus 60. So it will be 15, which will be 0.015 meters, and the Y will be the same thing. Okay. So now we're first going to find the normal stress. So the normal stress will be on the X direction. Okay, and if we look at the figure on top, you will have a normal stress on the X direction due to the moment created by this 13, which is 13 times 0.4 will be the 5.2, which is this one. So this one will be going down, no? Yeah, this cross section will be bending. So will point A and B be in tension or compression? Will be in tension. So we can write over here tension. So we know that should be negative. So we have what? M. So this 13 force will create a moment about the Y. So it will be MBY. If this is MBY, what do we need to use now? We need to use the Y location, no? Wait, let's be careful here. No, sorry. The 5.2 is MBZ. I mean, we can start by MBY, it doesn't matter. But if we do MBY, this would be the moment created by the 9 kilonewton force. 9 times 0.4 is 3.6. So this will create a moment in that direction. So this will be bending this way. So A and B will be what? Tension or compression? It will be bending this way, no? Do you see what I'm talking about? When you pull this force, this side will be the concave side, no? Yeah. So which side? This side should be what? Tension or compression? Talking about this, the moment created by the 9. So this is bending away from there. And this is, the back of this is over here. So A and B would be in tension as well. Okay. We have MBY. If we start by MBY, now the cross section will be moving, changing on the Z direction. And this will be bending about which axis? About the Y axis. Okay. We have here I of Y. So this one will be in tension. So we keep that one positive. Then we already said that the other one that will be MBZ is this one right here, created by the 5.2, 0.4 times 13 will be 5.2. This one is going down. So A and B we say was going to be also in tension. Okay. So these two values, we're going to take the positive value. MBZ now will be changing in function of Y, will be here. And this will be bending about the I of Z. I'm recording. So now what do we have? MBZ is equal to 5.2 kilonewton. So let me multiply by 3 right away. MBY is 3.6 to the 3. Then we have, let's say here, YA is equal to 0.0375. ZA, this is for the points, equal to 0.075. YB is equal to YA. And ZB is equal to 0.050. All right. Now, from before, we know that I sub Z is equal to what? I sub Z we calculated to be equal to 3.9303 10 to the minus 6. So 3.9303 exponential minus 6. And IY equal to, how much was it? 7.3215. 3215 to the minus 6. So you see, we could spend a lot of time doing the hand calculations. So let's say SG of point A will be equal to what? BY times ZA divided by I of Y plus MBZ times Y of A divided by IZ. And the stress at B will be the same thing, but with the coordinates P over here. Okay, so stress at A would be 86.492. So let's say point A. Let me go to another page. So let's see, we can write over here at points A and B. What do we have? Sigma x at point A will be equal to MBYZ of sub A divided by I of Y plus MB of Z Y sub A divided by I of Z. And this is going to give us a result of 86.492 10 to the 6 pascals, or this will be approximately 86.5 megapascals. Okay, the normal stress at point B basically is the same expression. You just replace by point B. And this is going to give you 56.99 10 to the 6 pascals, or sigma x at point B approximately equal to 57 megapascals. Okay. All right, the next thing we need to calculate is the shear stress. So remember, this time we know that the expression for the shear stress is VQ over IT. And again, let's do a quick figure. Okay, so this is point A, point B. Again, this is 150. $75. Then the thickness of each one of the walls is 13 millimeters. And now remember, from this problem, we calculated Vy and Vx. Sorry, Vx, sorry, Vy and Vz. And here, what do you have? So this is pulling down. We calculated that the force inside the structure needs to be on the opposite direction, no? Yeah? So we have a Vy going up. That should be equal to 13, probably is what we found. So we have Vy, so the loading is Vy equal to 13. And then this one is what? This should be a negative. So the inside the structure is going to be a Vy going on the positive Vz. So we'll have a Vz of 9. Again, this should be the same coordinate system, Y and Z. Okay. All right, so over here now, obviously, we're not going to do both forces at the same time. So let's concentrate into one at a time. So which one you want to do first, the Vy or the Vz? Vy, Vz, doesn't matter. Okay, so let's start maybe by the Vz, which is the most difficult. So let's see, due. So first, Vz only. So in this case, maybe you see here I did the figure using this coordinate system. All right, but really if we use this one, okay, let me just redo the figure very quick. Figures never hurt. So we know this is the neutral axis. This will be Y. And this is Z. So we're looking at the effect of what? In what direction will be the force? Vz is pulling in that direction. Okay? All right, and this is point A. And this is point B. Okay, so the equation to solve this one would be tau equal, leave some space here, V space Q divided by I space T. So basically, we know this is due to Vz. Q, I'm going to leave it as it is over here. The I should be what? Should be I of Y or I of Z? We move in that direction. This is crossing the eyes of Y, so it should be I of Y. And T will be whatever is the thickness order. All right, so keep the figure over here with you. So this is page 54. Okay, so we keep the figure with us. Okay, by looking at the figure, let's see if you understood what is shear. What should be the shear at point A? In order to have shear, what do you need? You need to have one surface against the other one, no? In the direction of the Z, is point A rubbing against anything else? Here there is nothing, no? If you look at the surfaces, so this surface here is nothing. So the shear at this location is 0. I mean, guys, this is solid. Again, if you have a rectangular cross section, what is the distribution of the shear? I think we said last time, 0 at the top of the bottom because there is no area to shear against. And where would be the shear maximum? At the neutral axis. Again, this is solid mechanics. We haven't done anything new. All right, so in this case, this is at the top, so shear is 0. Actually, going to be 0 no matter what, even for the other force. But this is simply because there is no surface. So really, if you look at the equation, Q sub A will be equal to 0. Now, point B. This will be V of Z, Q sub B, divided by I sub Y times T. Okay, I'm going to redo the figure. So if you have the force applied in that direction, what would be the areas resisting this force? If here was 0, we'll have this area, no? Yeah, but because there's a flange on top and the bottom, you could also assume that since the force applied in the middle, this will also resist the shear. Now, how did you calculate the Q sub A? It was, I'm not going to redo it again, is the area times the distance from the neutral axis to the CG of the area. So here Q sub B will be equal to what? Leave some space over here because I'm just going to add a 2. What is that distance? From here to here, that was 60 millimeters. So it will be 0.06 is 60 millimeters here. Times, what is the thickness? 13. So times 0.013. So this is the area. And now, the distance from the neutral axis to the CG, this is 75, so that gives us 37.5. From here to here, minus 6.5. How much would that be? Is it 31? Okay. What is the mistake that I've done? This is bending in direction. So really the distance we should be looking at is not this one, but this one here, no? That distance here, 31, will be looking at the Vy. So we're looking at that distance. So from the center to there. So that will be 75. So I think that was 150. So it will be 75 minus the center of this will be 75. So that will be 30. So 45. Yes, do you see that? Okay, so times 0.045. Be careful here again, is the horizontal distance, not the vertical. So this is times distance. All right, if we do the calculation for this will give you Q of B equal to 7.02 10 to the minus 5. And this should be meters to the cube. So now we substitute into tau of B equal to VZ Q of B divided by I sub Y. Oh, sorry guys. Again, since it's the top and the bottom, don't forget to put a 2 over here. And now here times T. So I'm going to write it down, everything, that way we're not going to miss anything. This will be 9 kilonewtons times 7.02 10 to the minus 5 divided by the I sub Y that we say was equal to 7.3215 10 to the minus 6. And now be careful here with the thickness, because the thickness is 2 times the 13. Okay, because it's this one and this one. And if you carry out this calculation, again, we could go and do it in the MATLAB, but I have it over here. This should be 3.32 megapascals. Okay, so not to confuse you over here, just to add for the understanding, I'm going to show you a different way to calculate, this tau sub B due to the VZ load, okay? So let's say, alternate procedure to calculate tau sub B due to VZ. Okay, so over here, everything's about the figure. So let's say I'm going to redo here the cross section. Okay, this is point B over here. This is our point B. And this is what makes shear difficult. Right? So let's say if we look from the top, you will agree that all this area could also be the one in shear. So if you look at this, so neutral axis, VC is going in that direction. Okay, and all this distance here, all the way to the end, basically that would be the length of the beam, which is 0.4 meters. We go all the way to the end. This is 0.4 meters. All right. And now let me write it down. We calculate that this distance over here, which is the one I didn't do properly before, is 0.045. So basically it was the 150. So sorry, 150, 75 minus 30. Okay, we have 0.045. Is that this one over here? Okay, it's that distance from here to the middle of the cross section. All right, so if we now use the same equation, tau of B equal to VZ Q of B divided by I of Y T. But this time, we're going to be using. So VZ will be the same thing, 9, 10 to the 3. I sub Y will be the same thing, 7.3215 10 to the minus 6. But now what's going to change is the Q and the T. So if we look from the top, what would be this area equal to? This would be 60 millimeters times the 0.4, no? So this will be, let's say, 60 millimeters will be 0.06 times 0.4, so this area over here. And now the distance should be the same one, which is the distance from the center of the neutral axis. So if you want this neutral axis this way in this case, it is 0.045. And this time, what will be the thickness? The whole length of the beam will be 0.4 meters. Okay, so let's do the calculation and then I'll stop for a second and I'll explain it, okay? So if you substitute into the above equation, so let's say tau sub B would be equal to 9, 10 to the 3 times whatever this value is over here, 0.06 times 0.4 times 0.045 divided by the 7.3215 10 to the minus 6 times 0.4. If we didn't do anything wrong, we should get exactly the same value. Can somebody go and check, please? So we should get 3.32, something like that, 10 to the 6. All right, as before. Okay, so why is this happening? Why can you calculate for one or the other, okay? The reason being over here, I'm gonna write on this page, but I'm not gonna keep it, is that if you do shear, if you do, probably in solid you did this, if you have a little block, all right? So the generally shear, the sign convention for shear is this way. Okay, so this is just a review. Why are those two forces in opposite direction and these two should be in opposite direction? so that we have summation of forces equal to 0, no? Otherwise, we'll be moving. Okay. So if this is the shear in this phase, what's going to be the shear on the other phase? It needs to be 0 also along this line, no? So you will have here shear force that will be in this direction, on the opposite direction. And then everything will get reversed over here. Will be this way, this one will be down, and this one will be going up. Does that make sense or no? So basically, the only thing that I'm trying to show over here is that you can, and the value of the shear over here, the tau blue and the tau red, should be the same one, no? So you should be able to calculate the tau looking at this phase, which is what we did the first time, or you should be doing to calculate the tau by looking at the top phase, which is what we did the second time. Yeah? Okay. So I hope that makes sense, okay? All right. So we did calculate the shear at point B and A and B. So at point A, we found that it's 0 due to VZ only. Now let's do the same thing by using VY only. So let's see, which way did I do this? Okay. So VY only. So once again, I'm going to redo the figure very quick. So this time, yes, this will be the neutral axis. Our force Vy going that direction, and it's 13. This is point A, this is point B. So here the equation would be tau equal VQ over IT. So in that equation, we have really it should be V is Vy equal to 9, 10 to the 3. I is I. So let's see, we have this is YZ. So the one resistant will be the Z. So it will be IZ, which we say was equal to 3.9303 to the minus 6. The thickness this time will be, all this area will be resistant, so the thickness will be the 150, so 0.15 meters would be all this length. Remember, shear, the area needs to be perpendicular, no? That's the definition of shear, no? Force perpendicular to the area, otherwise would be normal stress. And now, for this one, it's going to be very easy. Let's see if you understood. What is Q? What is Q at the top if the force is going this way? What should be the shear at the top? 0. So that will give you Q is equal to 0. So from here you will find that, so that tau sub A will be equal to tau sub B equal to 0. All right, so let's do a quick summary. So we found that the stress at point A to be equal to approximately 86.5 megapascals. And the shear is 0. At point B, we found the normal stress to be equal approximately to 57 megapascals. And the tau sub B will be just the tau sub B due to the VZ load. That is the one we calculated before, to be equal to 3.32 megapascals. So resume recording. So thank you for checking out my notes. Actually, you're right. This should be 13. Over here, we just did the 9, no? Thank you so much.